Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. So now we know how to find a derivative, which is the instantaneous rate of change. But there's a catch. A derivative doesn't always exist. Just because you have a function doesn't mean you can differentiate it everywhere. Today, we're looking at the concept of differentiability. What makes a function differentiable? And more importantly, what breaks it? Now, before we continue, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. And now let's start with a definition. A function is differentiable at a if f prime of a exists. It is differentiable on an open interval ab if it's differentiable at every number in that interval. So recall that the derivative of f of x is this limit here. So when we say a function is differentiable at a point a, it means that the limit of this difference quotient must exist. This also tells us that there is a hidden requirement, and that is the function must be continuous at that point, because if it's not continuous, then the limit's not going to exist. So you can think of differentiability as a higher standard than continuity, meaning all differentiable functions are continuous, but not all continuous functions are differentiable. In order to be differentiable, meaning we can find the slope of a tangent, the graph must be unbroken, which is the continuous part, and it must be smooth. There are three classic ways a function fails to be differentiable. Let's take a look at some examples. Case 1 is when it is discontinuous. So meaning if you need to lift up your pen in order to actually draw this graph, then that means you can't find the derivative there. So here, this function is discontinuous. So the limit part of our definition is going to fall apart. And this works for any discontinuity. So that would be a jump discontinuity, a removable discontinuity, and an infinite discontinuity. Now, the second case is when our graph has what looks like a corner. The reason that this is not differentiable is because if we were approaching this corner from the left-hand side, we can see that the slope is positive. It looks something like this. However, if we are approaching this corner from the right-hand side, the slope is negative. And since the slopes don't agree at that point, the limit fails. So therefore, this graph is not differentiable at this corner. And the third case is when we have a vertical tangent. So here, this graph looks continuous and it also looks smooth, but it gets infinitely steep. So right around here, we can see that we have a vertical tangent, which means the slope is undefined. So therefore, this graph is not differentiable there. And this is the same idea as when we learned about linear equations and how vertical lines have an undefined slope. And now let's take a look at an algebraic example. Here we have a piecewise function. So the first part is asking if the function is continuous at x is equal to 4. So recall the definition of continuity. Firstly, the function has to be defined at that point. Next, the limit has to exist. And finally, the limit has to equal to the value of the function at that point. Firstly, we can see that the function is defined at 4 because f of 4 is equal to 1 over 5 minus 4. So that is equal to 1. And this is because we can see that it is defined as 1 over 5 minus x for x greater than or equal to 4. Next, for our limit, we can see that if we are approaching 4 from the negative side, we're going to be using the top function. So this is equal to the limit as x approaches 4 from the left-hand side of 5 minus x, which is equal to 5 minus 4, which is equal to 1. And now the limit as we approach 4 from the right-hand side of our function, we're going to be using the bottom piece. So that is going to be equal to the limit as x approaches 4 from the positive side of 1 over 5 minus x. So this is going to be 1 over 5 minus 4, which is equal to 1. And since the left side limit and the right side limit are both equal to 1, the overall limit as x approaches 4 for our function is equal to 1. And this is equal to the function evaluated at 4. So therefore, we can say that, yes, it is continuous at x is equal to 4. Now, the second part of this question is asking if the function is differentiable at x is equal to 4. So this means we need to find the slope of the function as we approach 4 from the left side, and we need to find the slope of this function as we approach from the right side. So then for the left side, this is going to be limit as h approaches 0, and the function that we're using is the top function, so that'll be 5 minus x plus h minus 5 minus x, and this is over h. So then we can go ahead and simplify our numerator. So we get 5 minus x minus h minus 5 plus x. And then we have this is over h. So the 5's will cancel and the x's will cancel, and we're left with negative h over h. So this is equal to negative 1. And now we're going to do the exact same thing, but we're going to find it for the other piece of the function. So that's going to be limit as h approaches 0 of, we're going to get 1 over 5 minus x minus h minus 1 over 5 minus x. And then this is over h. Next, we're going to put our numerator over a common denominator. So we get limit as h approaches 0, and then we are going to get 5 minus x minus 5 minus x minus h over 5 minus x minus h times 5 minus x. And then this is over h. And now we can go ahead and simplify our numerator a little bit. So that's limit as h approaches 0 of 5 minus x minus 5 plus x plus h. And then we're going to combine the denominator. So we get 5 minus x minus h times 5 minus x times h. But now we can cancel out the 5's and then the x's, and then we're just left with h on top, which we can cancel with the factor of h in the denominator. So this becomes limit as h approaches 0 of 1 over 5 minus x minus h times 5 minus x. And now we can go ahead and take our limit, and this becomes 1 over 5 minus x squared. And now we have our two pieces. So if we are looking for the derivative or the slope of the function as we approach 4 from the left side, it's going to be this first limit up here. So if we look at f prime of 4 from the left side, that is going to be equal to negative 1. And if we're looking for the slope of our function as we approach 4 from the positive side, we're going to be using this bottom limit. So that is going to be 1 over 5 minus 4 squared, which is equal to positive 1. And since these two are not equal to each other, that tells us our function is not differentiable at x is equal to 4. And now let's do a recap of what we covered in this video. We learned the definition of differentiability. It means that a derivative exists at a point. We also saw how it's a stronger condition than continuity, meaning a function must be continuous in order for it to be differentiable, but continuity alone is not enough. We saw geometrically that differentiability means smoothness. So at a differentiable point, the graph has a well-defined tangent line with a single finite slope. We went over the 3 common reasons where a derivative fails to exist, which are corners or cusps. That's when the left and right slope don't match. Discontinuities, which is where the function breaks. And finally, we have vertical tangents, which is where the slope becomes infinite. And again, just to reiterate, continuity does not guarantee differentiability. Even when the limits agree and the function is continuous, the derivative can still fail if the slopes from each side do not match. However, if a function is differentiable, then it is continuous. And now it is your turn to give this a try. Can you find the solution to the question on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.